Okay, so just had some questions about some homework, so on antiderivatives. Okay, so the first question is to find the function where you know its derivative is square root of x times 3 plus 5x, and you know one of the points, you know the point 1, 9 lies on the graph f. So from last time, remember that there's no real antiderivative rule for products. However, we don't need to treat this as a product, right? If we just distribute the radical x, then we can treat it as just a power. So this is 3x to the 1 half plus 5x. And then what's the power of x here if I put this in exponent notation? X radical x is what exponent? Well, it's x to the 1 times x to the 1 half. So that makes x to the 3 halves, yes. Okay, so this is the derivative. So we know that the antiderivative of f prime is f. So f of x, its antiderivative, has the general form, and now we use the power rule of antiderivatives. So can someone tell me the antiderivative of x to the 1 half using the power rule? Or can someone just tell me the power rule and then we can figure it out from there? Whichever one. So close 3 halves, but you want it be divided by 3 halves. So you want 3 and then x to the 3 halves, but we divide by 3 halves. So this really comes from, if you want to do 1 half plus 1 over 1 half plus 1. That's using the power rule. So just remember, you divide. So in the derivative, you multiply by the new power, the power. Here we're dividing by the power. So this is 3x to the 3 halves over 3 halves, and then which is 2x to the 3 halves. Okay, so let's do the same thing for the antiderivative of x to the 3 halves. So what would the antiderivative be? So you can just tell me the power and then what you divide by. Yes, 5 halves. So it's x to the 5 halves over 5 halves. And yes, that does simplify down to 2x to the 5 halves. And this is all plus c. All right, so now we know a specific point on the graph. So this is the form of any function whose derivative is radical x 3 plus 5x. So a theorem that we had last time is that antiderivatives are unique up to a point. Or I could say it as are defined by a point. So what does that mean? Just plug in 1. F of 1 is equal to 9. That's part of our given. So when you plug in 1 into the function, you get 2 times 1 plus 2 times 1 plus c. So you have 9 equals 4 plus c. So 5 is equal to c. So what is the answer? F of x is equal to 2, you can say cube root of, not cube root, square root of x squared, or cubed, plus 2 square root of x to the 5th, plus 5. So that's the answer. All right, is that better? Seeing that out for for those who confused by this? Yeah. So general scheme is find the antiderivative. So this is the general antiderivative. So the general antiderivative is kind of infinite amount of functions, right? C can be anything. But if you know just one point, then you get an actual like a specific function, right? Because we know that no two antiderivatives intersect anywhere. So if you know one point on the antiderivative, then you know all the points. Okay, so let's do another one that was asked. Okay, so we have a stone that is dropped off a cliff and hit the ground with a speed of 136 feet per second. So the question is, how high is the cliff? Okay, so this is just understanding the relationship between speed, acceleration, and velocity. So before even attempting the problem, let's just review some derivatives. If s of t is position, and you take the derivative, what do you get? If you take the derivative of position, what type of thing do you have? Right, you get v prime, or you get v of t. Velocity is the derivative of position. Okay, so now let's take the derivative of velocity as a of t. Okay, so if we know this relationship of derivatives, then if we go backwards, what action brings us backwards? So if you undo a derivative, what are you doing? What do you call that? Yeah, that's the definition of antiderivative. There's one thing, though, when you take the antiderivative, is the antiderivative a v, or is there something you need to kind of up to what? Like, is the antiderivative a of t exactly v of t, or is it anything else? Yeah. So in general, we have a plus c added here. Now, if we take the antiderivative one more time, what is the arbitrary terms here? So if we take the antiderivative of something plus c, yeah, there's going to be two things going on. First, you take the antiderivative of c, and then there's antiderivative constant term. Okay, so let's use this fact to solve this problem. So we know the acceleration constant is 32 feet per second. That's the given. So I think this is like the 9.81 meters per second, and that's in metric. So if I know that the acceleration is constant, right? There's no like rocket propellers, right? You're just dropping it. So let's take so we know that the antiderivative of acceleration is velocity. So what is the antiderivative of 32 feet per second? You don't need units. Just what is antiderivative of 32? Yeah, 32x plus c. 32x plus c. Now, look at 32x plus c. Do you agree that it's 1-to-1? Like, what kind of graph is 32x plus c? It's linear, yeah. So would you agree that when v of t is equal to 136, t is unique? Like there's only one t where v is 136. Yeah. So we don't have to worry about it. There's only one point in time where the v is 136. It's when it hits the ground. Okay, so we'll keep that in mind. Okay, so what we want to find is position, right? Because we want to find how tall the cliff is. So if we can calculate how long it takes for it to hit the ground, then if we plug that time into position, we can calculate the height of the cliff. So what is the antiderivative of velocity? It's position. So what's the antiderivative of this velocity term? Like, what is s? Yes, it's 16. Yes, 32t squared divided by 2 is 16, then plus cx, and then plus d. C t plus d. Okay, so let's think about some facts. What's v of 0? What do you think v of 0 is? Yeah, why is it 0? Right. All it says is the stone is dropped off a cliff, right? It's not thrown off a cliff. It's not, it's not thrown off a cliff. So there's no initial there's no initial velocity, right? It wasn't falling before and then it continued to fall, right? The initial velocity is 0. So we can use that fact to solve for c, right? Because we know that antiderivatives are unique up to a point. So v of 0 is equal to 0, which is initial velocity, was equal to 32 times 0 plus c. So that means c is equal to 0. So this changes our position. So our new position function is s of t is equal to 16t squared plus d, because c is equal to 0. Okay, so now that we know, and also we have new velocity, right? New velocity is just v of t is equal to 32t. Okay, so now that we know that v of t is equal to 32t, what can we do with the 136? We can actually calculate it now, right? So if v of t is 136, then we can exactly find out what t is. So I cannot do that in my head. So what is that? 136 divided by, yeah, thanks, for 4.25. Okay, so what is special about this t? What does solving for 136 do? What happens at time t equals 4.25? Yeah, this is when stone hits the ground. Right, that's because that we know that the stone hits the ground at 136 feet per second. And by our little comment here, there's only one place where the velocity can be 136. So if we know when that is, then we know when the stone hits the ground. All right, so now, okay, actually, someone tell me, what is d? So let me ask this instead. What is s of 0? Initial position, yeah. So there's two things that we can do. This one I think is maybe the clearer one. If you want to let s of 0 equal 0, then what does s of t measure? So if you set your initial position to be 0, then what is the new s of t a measure of? Good. Yeah, it's displacement from 0. So in the problem, what is s of t? What does displacement from 0 mean in the problem? So how do you interpret s of t if you know that it's displacement from 0? What would that mean, like, physically? Like, how would you describe that physically? So here's the cliff. And here's the ball that's dropped. So we're saying that this is like our x-axis here. Like what's the point here? This is some point in time, right? So when you calculate s of t at this time, you're calculating how far the ball has dropped at that point in time. How far the ball dropped, or the stone dropped at that point in time. Okay, so that means, how do you find the height of the cliff then? If s of t measures how far the stone dropped at some point in time, what is the height of the cliff? Oh yeah, so first we need to, well, if we let s of 0 equal 0, then d is equal to 0. So it's kind of like normalizing our starting place. Then, yeah, so then the answer is plug in 4.25. Right, 4.25 was when the stone hits the ground. And so whatever that answer is the height of the cliff. Okay, so any questions on that? So it's kind of interpreting, I think the biggest thing with kind of these antiderivatives is knowing how to define a point, because antiderivatives are unique at a point. So if you know how to solve for a specific point on the graph, and interpreting what that means on the graph, then you can get like the physical part of it after that. Okay, so any questions on that? Okay, so today we're going to talk about area underneath the curve. So I just have some examples here that we can look at. I think we know how to find the area underneath these curves. So the goal is to find the area that's bounded between the function f of x, the x-axis, and the endpoints. Is there going to be a question like this one? Maybe. I mean, just notice that I kind of I'm over-explaining things because, I'm trying to get you to understand. But you could pretty much reduce this problem into a couple of lines, right, if you kind of get the main ideas. So the biggest thing is just this is the most information that we have that was kind of really needed, right? Which isn't too bad. And then from here, we were just talking about what does it mean when we plug in 0, and interpreting that, and then solving for. So don't be too scared that it seemed long, because the big things that mattered were this stuff here, this chain of antiderivatives. So we're, I mean, still practice, of course, but it doesn't need to be that long. That helps. All right, so for the remainder of the class, we're going to talk about how to find the area underneath the curve. So we know geometry, so we know some of these answers just based on geometry. All right, so can someone tell me how to find the area underneath the curve for this first one here? So I want to find the area underneath y equals 2. That's bounded between the x-axis and the endpoints 0 and 1. So how do I find the area? Yeah, so x times y. So what's what? What's x? What's y? This is a specific region. So when you mean x times y, you probably mean length times width, right? Yes. So the length of the width of this rectangle is 1, and the height of this rectangle is 2. So the area is 2 times 1 is equal to 2. All right, cool. So let's do this one. Find the area between y equals a. So now this is more general. The x-axis and the endpoints b and c. So what is area of this region here? So we have length times width. Good, yeah. So since y equals a, that means this vertical length must be a, and this horizontal length is c minus b. So then when you multiply it, you get a times c minus b is the area. Okay, questions on that? Just area of a rectangle? Okay. Let's do this. Find the region bounded between y equals x, the x-axis, and 0, 1. Okay, so what is the area of this thing? X over 2. X can be anything though, right? Yeah, so maybe if it was like 0 to a, that would probably be a over 2. Yeah, yeah, so it's the area of a triangle is base times height divided by 2. So that's 1 times 1 divided by 2 is 1/2. Okay. Now with this one, we have y equals ax divided, and on the line interval endpoints BC. So there's a couple ways to do this. Someone give me one way. Just want to find this region. Yeah, that's one way. You just split it into a triangle and a square. So what is the area of the rectangle? So first we have this length, which we said before was c minus b. So we just need this length. AB, good. Right, because this point here, the y value is AB. That's AB. So we have AB, C minus B here. Okay, so now we look at the triangle. What is the area of the triangle? So we know the base we established was C minus B. So all we really need to know is the height. Yeah, so the height is this whole line, which is AC, minus this line, which is we established was AB. So the area of the triangle is 1/2 base times height. So notice we can factor out a, we get a over 2, c minus b squared. So just remarking, there's something interesting about this ax and this here. Can anyone see something that looks similar between those two? This is the area. Just an observation about a similarity? Or how they're related, maybe? If not, it's okay. What if I replace c minus b with x? What would it look like then? What would the area be if I replace c minus b with x? What is this in relation to this? Yeah, that's the antiderivative. So right now it's a very weird coincidence. But so just keep that in mind. We'll prove why there is there is a relationship there. Okay, we can actually do this problem a different way. Can someone see a different way instead of splitting up into a rectangle and a triangle? How else we can find the area? Did anybody have a different approach? Good, yeah, you could do big triangle minus small triangle. So the big triangle is this one. And the small triangle is this one. All right, so so this one is easier in some regard because this is just a case of the first one where they both start at 0. So let's calculate that. So what is this area? It would be B is the base. The height is BA, yeah, over 2, right? This is BA. So you get AB squared over 2. So now let's do the the bigger triangle. So all we really need to know is this height. The base is C, and then what is the height? Similar thing, it's AC. Okay, so if we subtract, which one? We subtract the bigger one, right? AC squared over 2 minus B, AB squared over 2. They both have an A over 2. We get C squared minus B squared. Let's see. That's not what we get though, right? Did oh, we didn't add the 2. Oops. Yeah, we forgot to add. So if you add it to A, B, C minus B, then that would be the answer. Sorry. Okay, so then we get this, and then you can just do some algebra to show that they're the same. Yeah. So anyway, it's another way of calculating the area by subtracting the bigger one from the smaller one, right? So then the answer is this stuff here, this trapezoid. Okay, cool. Let's do another one. So let's find the area bounded between the function, the x-axis, and the endpoints. So that's all this stuff under here. Okay, how do you do that? for square root of 1 minus x squared. All right, I don't see a rectangle. I don't see a triangle. What sort of thing is this? Yeah, this is a semicircle. So what is the area of a semicircle? Yes. So pi r squared is the area of a circle, and then divide by 2 because it's a semicircle. So what is r in this case? 1. So pi over 2. All right, cool. Let's do a more general one. So this is the general form of a circle lies a semicircle that lies on the x-axis. So this would be like A here. Okay, so what is the formula? What is the area underneath this curve? You don't have to think too hard about it. So why do you have a plus r? What does a plus r mean? Is it the radius? So if this is a here, this would be the radius, right? And this would be the radius. A plus r is this length here. That's a plus r. So this is r. Do you see that? It's not centered at the origin, so this is not the radius. The radius is just r. Same thing with a minus r. That's not the radius. This is not the radius, right? Here's another way you can approach it if the off center is confusing. So would you agree that if you translate to the left by a, that the area doesn't change? Do you agree with that? So let's both graph it and then look at what a translation does to the function. So if I translate to the left by a, where's the center of my circle? You take all the x values and subtract a, right? So take all the x values and you subtract a. So the center becomes the origin. It's a plus r just becomes r, and a minus r becomes minus r. And the semicircle shifts along with it. Now, how do you view that in terms of the function? What do you do when you do left translations? If you translate to the left by a, how do you change the function? Do you remember how to do left translations? Yeah, so when you do left, you add. So if you add a to x, because we're translating the x component, not in the y component, you add a to the x, so that just becomes r squared minus x squared. So now, viewing that, do you see why the area is pi r squared over 2? And has really nothing to do with a. Yeah, so the kind of the red herring here was the a. A doesn't matter. Right, since these are just same by translations. Okay, so questions just on how to find area underneath the curves just using some geometry? Okay, so for a lot of the rest of the class, pretty much this is like as much as we can do in geometry, right? We may be able to do something with ellipses, or maybe there's some formula for that. Maybe we can do something with like some polygons, if they're rigid edges. But when we get to curves, other than like circles, it's really hard to find the area underneath. So that's going to be, we're going to actually use calculus to be able to do that. So here I'm going to give a so we've been just talking colloquially about area underneath the curve, but let's kind of give the definition. So the area underneath the curve f of x between x equals a and x equals b is the area of the region enclosed by 4 things: f of x, x equals a, the vertical line, x equals b, the vertical line, and y equals 0, the x-axis. So these are vertical, and this is x-axis. So this is essentially what we were doing before, right? We're between the x-axis and these vertical lines and the function, we were finding the area underneath the curve. Okay, so something we didn't talk about, but we'll talk about it here, that area underneath, or area in the lower half region is considered negative. Later we'll talk about something called total area. Turns the negative areas into positive. Okay, so just some facts. All right, so like as a picture, if this is any function, f of x, the region between a and b, the area, is you take these vertical lines at a and b and the x-axis, and the area of the region enclosed, that is the area. Okay, so we did a lot of examples with things that we can do. So the question is, how do you even approach this? How do we even approach this? Well, how do we approach it? Well, we assume we know nothing, and all we know are these things here. These are the only things that we know about geometry for right now. Which of these shapes do you think is the most easy to work with? Like, if you want to, like, which was the easiest to do of all of these examples? Yeah, rectangles, right? There's not much to do with rectangles, right? So we know rectangles. So what we can do is approximate. Approximate area by rectangles. So maybe you could do this. It's not what we'll do, but notice that like this stuff down here and over here, these kind of look like rectangles. And then over here is, maybe we can think of it as this, this, and this, right? If you take the area of all the of this region bounded by these rectangles, then you'd think that's pretty close, right? Where, you know, it might be jutting out here, it's jutting out here and here. But do you agree that that's kind of close? How it kind of partitioned the region to kind of rectangles like that? So, I mean, that's not very an ordered way of doing it, right? I didn't really put any rhyme or reason to why I do those rectangles that way. So we're going to come up with a technique, and so maybe even like down here, it's not always, it's kind of underneath. So we're going to come up with a technique to how do you accurately approximate a curve, kind of come up with an algorithm. So does everyone understand like how rectangles can be used to approximate? Essentially, you are kind of fitting the curve into close enough rectangles. And we did it. We know how to find the area of this, the area of this, the area of this area, and this area. Those are easy to do, but the curve itself is hard. That's hard to do. So questions on the intuition there? Why rectangles are kind of the easiest, the most intuitive choice to do? They're like the most regular of all the shapes. They're kind of the easiest to work with. Right, with triangles, you have to deal with the base and the height, and they're in and like. But if you're like kind of off, you kind of have to deal with like a trapezoid. Circles, it's just kind of the formula is a little kind of confusing. If you want to try to approximate, may not want to do that. So let's come up with a technique to approximate something, with some regularity. Okay, so we're going to call this technique left rectangle approximation. So this is an algorithm. Okay, so again, this was kind of a messy approximation. We're going to come up with an algorithm that you can use for any function. Okay, here's the function f of x, and I want to estimate the area underneath the curve between a and b. Okay, so when I do some sort of algorithm, I probably want to keep things pretty consistent, right, or constant. So so what we want, what would make it very nice, if I were to approximate this with rectangles, how can I like simplify my my calculation? Yeah, how do you think? If area is length times width, and I want to approximate it with rectangles, so I'm going to add up a bunch of rectangles. What would what would be a method to simplify calculation? Okay, so I think doing that would kind of lay in the realm of like just kind of something that may not work for all functions. Like, what if a function doesn't have a local min or a local max or something along those lines, or maybe it's not even differentiable, right? So the what I mean by what I want to regulate when I look at all possible rectangles is, wouldn't it be easy if all the rectangles had the same width, for example? If all rectangles had the same width, would you agree that calculation would be a lot easier? So why is it easier? Is because if the estimated area is length 1 times width 1 plus length 2 times width 2, if all the widths are the same, what can you do if all the widths are the same? Yeah, you can factor it out. So all you really need to do, if all the widths are the same of your rectangles, all you need to figure out is what the lengths of your rectangles are. So that's what we're going to do. We're going to let all the widths of our rectangles be the same. Okay, so let me ask you this. Let the widths of the rectangles lie on the x-axis. What widths do they need to be? If you want to fill up the interval with n rectangles. So I want to fill up the interval with n rectangles. So each of these is going to be a width of a rectangle. So if I want to evenly divide this into n pieces, what is the width of each rectangle? I remember I want the widths to be the same. Yeah. So you take the length of the interval and divide it by the number of rectangles. Right? B minus A over n, it will be the width of each rectangle. And just kind of check that, right? If you do B minus A over n plus B minus A over n plus, what does that equal? If you add B minus A over n times, what does that equal? Yes, b minus a. Right? 1/nth, 1/nth, and then you have n nths. N of them. So that's b minus a. And that's what makes sense, right? If you want to add up all the widths of the rectangles and you want them to evenly distribute over the interval, that verifies that b minus a over n should be the width. Okay, so by doing that, we have we're going to make calculation a lot easier because all the widths are the same. So now we just want to figure out what are these L's. So there's going to be two methods to figure out the L's, and one of them is something called left approximation, and another method is called right approximation. So let's start with left approximation. Okay, so notice that in your first width, what is this point here? If the width of the rectangle is b minus a over n, what is this point here? The width plus a, yeah. So like a plus b minus a over n. So how do we define left angle approximation or left rectangle approximation? So for the estimated area as W times L1, L2 up to Ln, L1 is going to be defined as f of a. So in this first rectangle, we are going to look to the left of the width interval. So take a width interval and look at the leftmost point. So I'm looking at A. The height of this rectangle is going to be defined as f of a. So in other words, you're going to draw a straight line up until when you hit the curve, and that's going to be the height of your rectangle. Everyone see that? So now to make it a rectangle, this is going to be one of our rectangles in our approximation. Is that okay? So what do I mean by left? I look at the interval, and then the point I choose to plug in f is going to be the left of the leftmost endpoint. Okay, so what do you think L2 is going to be? So in the next rectangle I create, so the rectangle right next to it, which height do you think I want? Yes, the parentheses were confusing. Yeah, so it's going to be, it's this thing that we want, right? A plus b minus a over n. Because that is the left of the width interval. So this is our width interval, and this is the left point. So I take a new line and I draw a line up until I hit the curve. That's like right here. And then I draw a rectangle. Oh, shoot. I didn't want that. There we go. Okay, does that make sense? So this is left of the next one. Okay, so someone tell me L3. What is the height of the rectangle, of the third rectangle? Yeah, I add another width. So a plus 2b minus a over n. So I go from this, so this one is going to be 2b minus a over n. Draw a line up until we hit the curve, and draw a rectangle over. Okay, so I do this a bunch of times until I reach the last rectangle. What is the width of the last rectangle? Sorry, the length of the last rectangle. So is b to the left of the interval? Is the left endpoint? F of b is this one. B is the right one. So I want the other one. Right, I would want to graph it from here because that's the left of the endpoint. Yeah, b minus w. Or a plus n minus 1 w, good. So b minus a over n, or equivalently a plus n minus 1 times b minus a over n. Okay, so this is called, so now what do we have? What do we get? We get an approximation of the area. So I could just draw the intermediary ones here. So this would be the approximated area using this algorithm. It's not the only one, but this is n algorithm. So it's depending on how accurate you want to be, the number of n's would increase the accuracy. And that's not too hard to see. So that's the estimated area. Using this approximation. So more rectangles, better estimate. Why is a better estimate? Is that you're squeezing closer and closer to the curve. So if I like divided everything by 2, if I divided the n by 2, I would get new rectangles in between that hug the curve even closer. Okay, questions about that? So if you want a formula, a strict formula, so the estimated area is going to be W f of a plus f of a plus w plus dot 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 f of, you can say b minus w. So that's the formula for the estimated area, where w is equal to b minus a over n. Later, we're going to call w delta x. But for now, that doesn't really mean anything. But later, we'll call that delta x. Here's why we don't use the middle of the width. Oh, well, that's another approximation. That's a good one. That's actually a whole other approximation. We'll talk about that later. But I like that you brought that up. Yeah, so if we look at the if this is my partition of the widths, yes, you can define the height as the midpoint. And then you go out to the side and out to the side. And then this whole thing will be your rectangle approximation. So where your f now is the half of, so it'd be a plus w minus a over 2. So the midpoint. Yeah, so this is particularly called left endpoint, left rectangle approximation. So the left means where is the height? So as you can imagine, when we do right rectangle approximation, we're going to define the height of a rectangle to be the rightmost endpoint. So what you just described is called midpoint approximation, which defines the height of your rectangle to be the midpoint. So it turns out the midpoint is actually more accurate than the other two in general. However, calculation might be a bit harder because you have to take these averages every time. But that's a good observation. Yeah, midpoint is certainly valid. Yeah, cool. Does that answer your question? So you absolutely can use the midpoint, and we will later. But so this was specifically for left. So yeah, let's do right endpoint. We will talk about midpoint later. Because it's actually easier in some cases to use left and right. When we eventually calculate exact area, right, and it doesn't matter which approximation method you use, because so you just want to use the easiest one. All right, so let's use the right endpoint method. And it's really going to be the same thing, but we're going to choose the opposite, right? Here we chose the left of the width interval, and here we're going to choose the right of the width interval. So the widths are still going to be the same, but our lengths are going to be a bit different. Okay, so if we have this rectangle, if this is my width of the first rectangle, by the name, what do you think L1 is going to be? The length. A plus W, yeah. Because that's the right of the interval. Right endpoint of interval. So you draw your line up to the curve, stop, and then draw a line over to A and go down. So just by the same reasoning, you're going to keep on doing this until you get to the end. So tell me what the f value of the end will be. The last rectangle. F of b. That one's f of b. So I honestly like to start with b first when I do the right endpoint approximation, just because it's kind of easier to start from the right. Yeah, so this last one, I'm going to start from b and go up and then go over. Just f of b, not b minus w. Yeah, so this, all this is the area approximated. So this one was 5 rectangles, so it would be b minus a over 5 is each width. So the estimated area is w f of a plus w plus f of a plus 2w plus and dot f of b. So notice that the right and left endpoints calculation, it looks a lot similar. Looks pretty much the same, right? Here we start at f of a and then stop at f of b minus w. Whereas for a right endpoint, you start at f of a plus w and end at f of b. Okay, so questions on left versus right? And everyone see why it's a valid method of approximation? It's pretty regular, right? We're not partitioning the curve in such a way that kind of would make it hard to calculate, but it's pretty regular. All the widths are the same, and the lengths are just values of f. And we know what f is. All right, so let's actually do a calculation. Approximate area under y equals x squared. So we don't know what shape that is. Well, it's a parabola, but geometrically we don't. On 0, 1. Okay, so that's the parabola, and we're going to approximate it using rectangles. So let's approximate with 5 rectangles. Do 4 rectangles. Okay, so someone tell me, what are the widths of all my rectangles? If I want to use 4 rectangles, and I want to use this nice algorithm where all the widths are the same, what are the widths going to be? 0.25, yeah. So my widths, I'm gonna say the notation delta x, but I'll just use them interchangeably because I want to introduce that notation, but just know that I mean width every time. Yeah, I'm gonna use 1/4. Okay, so we have 1/4, 1/2, and 3/2. Okay, so these are my intervals. So let's use left approximation. So the area is going to be width times L1 plus L2 plus L3 plus L4. Okay, so let's do it. What's L1? What is the first rectangle? This is kind of a funny one. So what is the endpoint that I use? What do I plug in? 0. Yeah, that's kind of funny. So there's really no rectangle here. So this is the rectangle. So there's zero length. Okay, so now the next one, it's a bit more interesting. What would the length of the first real rectangle, but the second rectangle be? And what do you plug in? We'll just give the x value, and then we can. Good, yeah. So you're going to plug in 1/4 into the formula. So you bring the line up to hit the curve at 1/4, and then come over and down. So that's the length of that rectangle. And so for right now, we'll say f of 1/4, or let's say f of 0. And then the next one, it's going to be f of 1/2. Yep. And the next one, did I put 3/2 there? I meant 3/4. The next one, f of 3/4. Right, good. So this is the area, the approximated area using the left rectangle approximation. Okay, so let's calculate that. Okay, 1/4, 0 plus 1/16 plus 1/4 plus 9/16. Okay, so I'm going to do a little trick. Let's put everything over 16. Uh, 4/16 plus 9/16. Now, what happens if you factor out by 1/16, right? Everything in the fraction has a common factor of 1/16. So what happens if you factor out a 1/16? What remains in the parentheses? Just the numerator terms, yeah. So this is just 4/16 squared times, what's that, 14. So 4 times 14 over 16 squared. So 16 squared is just 4 to the 4th power. So it's 14 over 4 cubed, or 7 over 2 times 4 squared, which is 7 over 8 times 2, 16. Can someone plug in 7/16 into the calculator? Oh, wait. 7 over 32? Did I make a mistake? Sorry, why is it 2 times 4 squared? Oh, 4 squared is 16. Oh, silly. Thanks. 32. Yeah, so sorry. What's 7 over 32? 0.21. Okay, cool. Okay, so let's use it with let's use right approximation now and see what we get. So same intervals. Now let's use right approximation. Okay, so what is L1? F of 1/4. So you go to the right of the first interval, and then f of 1/2, and f of 3/4, and then f of 1. F of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1. So 1/4, and then we have 1/16 plus 1/4. Yes, remember this is y equals x squared, so that's why we're getting 1/16, 1/4, 9/16, and then 1. So if I factor out a 1/16 here, yeah, if I factor out 1/16, we get 1 over 4 times 1 over 16 times 1 plus, now if we factor out a 1/16 from 1/4, you get 4, because you're really multiplying by 16. Multiply 16 to 9/16, you get 9. Multiply 16 to 1, you get 16. So what is that? 13, 14, 16 is 30. 16. So is that 15 over 2, 16? I think that's good enough, right? 15 over 32. Okay. Does that look right? So what is that approximately? Approximately 1/4? Oh. 0.46, that's what I got. Yeah. So I'm going to spoil it for you, but I'm going to give you the actual area, which is something we'll figure out. The actual area is 1/3. So notice that our right approximation is bigger. 0.46 is bigger. And our left approximation was smaller. Now, you can see that by the picture, right? When you do the right approximation, the curve lies completely inside, right? So the actual area is actually a lot smaller than the right approximation. Similarly with the left approximation, there's a lot of the area that we left out. So what the actual area is somewhere close. It's somewhere closer to 1/3. Okay, so can someone tell me how we could get closer to 1/3? How could we get closer to the actual area? Yeah, we could do midpoints, but maybe we don't want to do midpoints yet. And it's not necessarily going to be the average, so we don't know how far apart they are from 1/3, or from the actual, respectively. So I used 4 rectangles here, right? Yes, yeah, so if I make the width smaller, that would be equating to adding in more rectangles. So here's the kind of the calculus assumption. We'll talk more about this later, but I don't really want to go into it too much right now. As W goes to 0, the estimated area approaches the actual area. Now, what's kind of interesting is that it's this kind of like, we can think of it as like squeeze theorem. So notice that the actual area is always in between the for x squared. May not be true for all of them, but the actual area for x squared is always in between the right approximation on n rectangles and the left approximation on n rectangles. So the claim is that if we bring n to infinity, which is equivalent to saying that w is going to 0, and we bring n to infinity and w goes to 0 for the right approximation, if these things are the same, maybe they're 1/3, we'll show that, then would you be safe to conclude that the area under x squared is 1/3? Do you agree that the actual area of x squared is always above the left approximation and always below the right approximation? Yeah, so we're going to do that. So we may not finish today, but I want to do at least, I haven't decided yet, but at least one of the left or rights. But we'll show that as the number of rectangles go to infinity, or the width goes to 0, the area is going to converge to 1/3. Okay, so the big question is, how do you do that? So let's think about it. Let's use left approximation. So let's say I want my W, my W is B minus A over N, right? And we know that our widths, or the lengths of our rectangles, is defined by, so we have B minus A over N times F of B minus A over N, or sorry, what is B minus A over N? This is an actual question. This is y equals x squared from 0 to 1. What is B minus A over N? We know what it is. What are the widths of all my rectangles if I want n of them? 1, yeah. So n rectangles. So the idea is that we're going to come up with an expression for the area in terms of n, and then we're going to take a limit. And the limit is going to be supposedly the actual area. So my W is 1 over n. So for my left approximation on n rectangles, so this is this thing, and we're going to make these smaller and smaller and smaller. It's going to be 1 over n, and then what is f? What is the first f? What's the first length? Oh, yeah, so what's a in this case? 0. So we start from 0, and go 1 over n, and keep going. And then what's the last rectangle we have? It's 2 ways of expressing it. Yeah, so you could have f of 1 minus 1 over n, or f of 1 or 0 plus, we're going to use this one, but it's other way around. It's n minus 1 over n. Right, if you add, it's okay. If you added one more n, you get 1. Okay, so what is this? This is 1 over n, and then we have 0 plus 1 over n squared plus, what's the next one, is 2 over n squared, then 3 over n squared plus n minus 1 over n squared. Okay, as I write it out, what's common between all these factors? Or not all these terms? What can you factor out from all these things? N? Yeah, the 1 over n squareds you factor out. So let's factor out all the 1 over n squareds. We get 1 over n cubed, then 1 plus 2 squared plus 3 squared, n minus 1 squared. Okay, good. We have time, so I can do this. So the question is, what is this? So for those of you who are pursuing computer science, this is a kind of a regular exercise and probably a good test question. So I'll show it to you. How do you calculate the sum of squares? Calculating the sum of squares of square integers up to an arbitrary value. So in this case, it's n minus 1. Okay, yeah, we'll do sigma notation later, but this is yes, this is equivalent to saying this. So we don't know this yet, but that is what it's saying. Sigma notation. So this notation comes later. Notation later. So that we're gonna calculate what that is. This is some n stuff. This is some function in terms of n. We can simplify it. Is that what you mean with the sigma notation? That is what this sum is in terms of the sigma notation. So we're actually going to calculate this. This is a formula. But let's prove it. So first, to start talking about the sum of square integers, we want to first start talking about the sum of integers to an arbitrary value. So what I mean is 1 plus 2 plus 3 plus keep on going plus n. What is this? This is equal to some number, right? If you plug in, if n is equal to 3, this would be equal to 6. If you plug in n equals 4, it would be, what, 10. So there's actually a formula that we can figure out. What is the sum of integers? So if you know sigma notation, this is solving this sum. So let's do it. Okay, so what I'm going to do is say, okay, I'm going to look at 1 plus 2 plus 3 plus all the way to n. And let's call this equal to sum. Now, what I'm going to do, let's express this in the reverse way. Let's start with n and then work our way down. So my first term is n. Then what's my second term? So think of this like factorial, but with addition. Yeah, n minus 1. Then what's my third term? N minus 2, yeah. And let's keep going. What's my second to last term? So I work my way backwards. What would my second to last term be? 2, yeah. 2 and then 1. Okay, so this is the same thing, right? That's also the sum. All I just did was rearrange the addition. We know addition is commutative, right? So I can range it however I like. Okay, now we're going to do a magic trick, and we're going to add these two things together. What is the sum of each column? If I draw the columns like this. What's the sum of each column? N plus 1. How many times did I add n plus 1? It's n times. Why is it n times? Because notice that the number of sums don't change if I group them this way, right? So there are n terms here, and obviously n terms here. So if I group them this way, this will be n terms here. Okay, so that's n times n plus 1 of them. Okay, sum plus sum is 2 of the sum. So it's n times n plus 1 over 2. Okay. Any questions on that? Okay, so if you're curious, just like if you add like k plus in this sum here, what happens at the random kth component? What you're going to be adding is n minus k plus 1. Right. Notice that each of these terms, what are these minus terms always in comparison to the upper one? It's always the negative of 1 less. So I'm always subtracting k minus 1. So that's why we get n plus 1 for all of them. So if you didn't like us just kind of filling in the blanks of n plus 1, when we arrange it this way, this is the formula for any component in between. Okay, is that okay for so the sum of the integers up to n is n times n plus 1 over 2. So for example, sum of integers up to, I don't know, 100. So that's 1 plus 2 plus 3 plus 100. So now you don't have to do that by hand. You just know that we figure out this formula that it's just going to be 100 times 100 plus 1 divided by 2. So that's 50 times 101. All right, so any questions on that? So that's 5,050. Okay, so let's do the squares now, because we need this formula for the sum of integers squared. All right, so again, this is 1 plus 2 squared plus 3 squared plus 4 squared up to n squared. Okay, so to do this, I'm actually going to go on an aside. And let's realize that we're actually going to use the cubic. Notice that n plus 1 cubed, how does this distribute? Does anyone have the formula for this distribution? This is like the binomial theorem. Well, if you use like Pascal's triangle and stuff like that, it's n cubed plus 3n squared plus 3n plus 1. So if you realize, so notice if you like subtract n cubed on both sides, you get an expression in terms of n squared and n. And we're going to manipulate that fact. Okay, so this is what we're going to do. Let's take this last line here, and let's add all the terms down to 1. So what I mean, the next term is going to be n cubed minus n minus 1 cubed. So by the formula, this is going to be 3 times n minus 1 squared plus n minus 1 plus 1. Can someone tell me what the next term is going to be? If that's the second term, what's the next term? What do I put here? Yeah, it's going to be n minus 1 cubed minus n minus 2 cubed, and it's going to be 3, and then we get n minus 2 squared plus n minus 2 plus 1. So I'm going to keep doing this until we get to 2 cubed minus 1 cubed yeah, we can stop there. 2 cubed minus, so let's maybe do one more before this. 3 cubed minus 2 cubed, and then 2 cubed minus 1 cubed. So what is this going to be? It's 3 times 2 squared plus 2 plus 1. And this one would be 3 1 squared plus 1 plus 1. Okay, so does anybody see the trick? What happens if we add all these up? First of all, someone tell me what the left-hand side is. Do you see something? Do you see a pattern on the left-hand side? Like, this simplifies to something. How about this? Can you see things that cancel? Yeah, all that's left is n plus 1 cubed minus 1. Because all these intermediary terms cancel from the line before it. But 1 never gets canceled, and n plus 1 cubed never gets canceled. So now, on the right-hand side, notice that all these terms have a factor of 3. So we can factor it out. What's inside? Look at what's inside. What do we know that's inside in the parentheses? If you add up all these terms in the parentheses, what values are there? On this side, we get the exact thing that we want, right? The sum of integers squared. And on this side, we got what we just solved for, right? The integers. So this, when you factor all this out, this is sum of integers squared, and this is sum of integers, which we know that formula. Now, someone tell me what this is. What's 1 plus 1 plus 1 plus 1, blah, blah, blah? What is this? N, yeah. How many times are you adding 1? You're adding it n times, right? There are n terms here, right? And you see that easily with this expression here. Okay, so we already solved for the sum integers. That was what we did before. So let's actually just expand this out. So we did this one up here. It's n cubed plus 3n squared plus 3n. We have a minus 1 and a plus 1, so that's it. So 3 times, the thing we want is the sum of integers squared. And we already solved for the sum of integers. That was n plus 1 over 2. Okay, now let's solve for s. Okay, so we get, if I subtract n on both sides, we get n cubed plus 3n squared plus 2n is equal to 3s plus 3n n plus 1 over 2. So now multiply 2 on both sides. We get 2n cubed plus 6n squared plus 4n is equal to 3s, or not 3s, because I'm multiplying by 2, 6s plus 3n n plus 1. So this is just 3n squared plus 3n. So if I subtract that, I get 2n cubed plus 3n squared plus n is equal to 6s. Now we divide by s, or 6. We get 2n cubed plus 3n squared plus n over 6 is equal to s. How do you factor the numerator? Take out an n, and then how can you proceed to factor? Yes, 2n plus 1, n plus 1. That's equal to s. So that is the formula for the sum of integers squared. All right, so we're pretty much out of time, but I just want to kind of, you could probably do it in 2 lines right now. So what did we end with in our attempt to find the general formula for the left approximation? We ended with the sum from 1 to n minus 1 squared. So we had 1 over, was it n cubed we had? 1 over n cubed, and then 1 plus 2 squared plus n minus 1 squared. So by the formula, this we just found is, so plugging in n minus 1, is n minus 1 2n minus 1 plus 1 times n over 6. So if you simplify that a bit, here's an n and an n, so I have n squared, and then n minus 1, 2n minus 1 over 6, right? 2n minus 2 plus 1 minus 1. Now let's distribute. 2n squared minus n minus 2n squared. Wait, what did I do? Sorry, minus 2n plus 1 over 6. All right, and someone tell me what this limit is. So this is the general formula, general left approximation formula for x squared on 0, 1. Now, what is the limit as n goes to infinity? And then we'll be done. what is that limit? Two sixths, which is 1/3. All right. Okay, so maybe next time we'll do the right approximations just to get the handle of the limits. Oh, okay. Yeah, I see. The notes aren't updating because I'm not signed in. So I'll sign in and then they'll be updated. Yeah, so next time we'll do the approximation on the right, and then that will definitively prove that the area underneath x squared from 0 to 1 is 1/3 by like squeeze theorem. All right, so any questions on this? I just think this is kind of cool stuff. Notice that we didn't actually need derivatives for this, right? We could have just done this after limits. We didn't even need to go through the derivatives to calculate the areas. But we'll find out that derivatives will come into play when we do integrals, which is all that's kind of like, we're pretty much doing integrals here, but we're doing it longhand. So we'll find a way to kind of make this shorter, but this is cool stuff. All right, so any questions, or shall we stop?